Dear students, let's take few more theorems in this chapter on Laplace transforms. The first is Laplace transform of integrals. If L of ft is equal to f of p, means if Laplace transform of ft is f of p, then Laplace transform of integral 0 to t fu du is given by f of p divided by p. Next one is regarding multiplication by powers of t. If L of ft is equal to f of p, then Laplace transform of t to the power n into ft is given by minus 1 to the power n into nth derivative of fp with respect to p for n is equal to 1, 2, 3 and so on. Now, if we take n is equal to 1, then L of t ft is given by minus d upon dp of f of p. Similarly, if L of ft is equal to fp, then L of t square into ft is given by d2 upon dp square into f of p. Next one is regarding division by t. If L of ft is equal to f of p, then Laplace transform of ft upon t is given by integral p to infinity fx dx, provided limit t tending to 0 ft of t exists. If this limit exists, then we can make use of this formula. And last result is Laplace transform of periodic function. If ft is a periodic function with period omega, then L of ft is given by 1 upon 1 minus e to the power minus p omega integral 0 to infinity e to the power minus pt ft dt. Okay, now let's take few examples based on these theorems. First example is find L of t cos at. That means we are multiplying by t. Now let's find out L of cos at. Now what is L of cos at? By formula it is p upon p square plus a square. So take this as f of p. So therefore L of t into cos at. So we apply corollary 1. L of t ft is minus d upon dp of f of p. So we have minus d upon dp of f upon p, f of p, which is minus d upon dp of p upon p square plus a square. So differentiate this using quotient rule. We will get this as p square minus a square upon p square plus a square whole square. In the next example, find L of t square sin at. Now L of sin at is given by a upon p square plus a square. Take this to be fp. Now there we have multiplied by t square. So L of t square sin at is given by, use this corollary number 2, d2 upon dp square f of p. So which is d2 upon dp square a upon p square plus a square. So again differentiate it 2 times using quotient rule. We will get it as 2a into 3p square minus a square upon p square plus a square whole cube. Third example, find L of t e to the power at sin at. Now f of t is sin at, then L of ft is L of sin at, which is a upon p square plus a square. Take this to be fp. Now we find out Laplace transform of t into sin at. So therefore L of t into sin at is given by minus d upon dp of fp, which is minus d upon dp of a upon p square plus a square. So differentiate it, we get it as 2ap upon p square plus a square whole square. So take this to be f1 of p. So therefore L of t into e to the power at sin at. Now we have multiplied by e to the power at. So therefore Laplace of this will be f1 of p minus a. Means wherever we have p, we replace it by p minus a. So we have 2a into p minus a upon p minus a whole square plus a square whole square, which on simplification it comes out to be 2a into p minus a divided by p square plus 2a square minus 2ap. Let's take fourth example. Prove that 0 to infinity t into e to the power minus 3t sin t dt is equal to 3 upon 50. So, we start with Laplace transform of sin t, which is 1 upon p square plus 1, which is equal to f of p. So, therefore, Laplace transform of t into sin t, use corollary 1. So, we have minus d upon dp of f of p, which is minus d upon dp of 1 upon p square plus 1. So, differentiate it using quotient rule, we get it as 2p upon p square plus 1 whole square. Now, this is Laplace transform of t sin t. So, by original definition, we have this as 0 to infinity e to the power minus pt t sin t dt is equal to 2p upon p square plus 1 whole square. So, therefore, here if we put p is equal to 3, looking at this what we have to prove. So, we take p is equal to 3. So, we have 0 to infinity e to the power minus 3t t sin t dt is equal to 3 upon 50. Now, we come to the problems where we are dividing it by t. So, prove that L of sin t upon t is equal to tan inverse of 1 upon p, and hence find L of sin a t upon t. Okay, let us do the first part. Now, suppose that f of t is sin of t. Now, if we take limit t tending to 0 f t upon t, which is limit t tending to 0 sin t upon t, which is equal to 1. Now, this is a finite quantity, that means this limit exists. So, therefore, if we take Laplace of sin t, which is 1 upon p square plus 1, which is equal to f of p, then by the theorem L of sin t upon t is given by integral p to infinity fx dx, which is integral p to infinity 1 upon x square plus 1 dx. Integral of 1 upon x square plus 1 is tan inverse x, p to infinity. Put the limits, tan inverse infinity minus tan inverse p, tan inverse infinity is pi by 2, tan inverse p is tan inverse p, and pi by 2 minus tan inverse p is cot inverse p, which can be written as tan inverse of 1 upon p. So, this is the first part. Now, in the second part, we have to find out L of sin a t upon t. So, multiply by a and divide by a. Okay. By this theorem, change of scale property, L of f of a t is equal to 1 upon a f of p upon a. We have Laplace transform this as this is a into 1 upon a tan inverse 1 upon p upon a. A gets cancelled. So, we have tan inverse of a upon p. Now, let us take 6th example. Find L of sin hyperbolic t upon t. Now, suppose that f of t is sin hyperbolic t upon t. Now, if we take the limit t tending to 0 sin hyperbolic t upon t, which is equal to 1, which is again a finite number. So, therefore, this limit exists, and now L of sin hyperbolic t is 1 upon p square minus 1, which is equal to f of p. So, therefore, L of sin hyperbolic t upon t is given by integration of fx dx from limits p to infinity, which is p to infinity 1 upon x square minus 1 dx. So, integrated, we have 1 upon 2 log of x minus 1 upon x plus 1, limits from p to infinity, which can be written as 1 by 2 log of 1 minus 1 upon x upon 1 plus 1 upon x p to infinity. So, put the limits, we will get it as half log p plus 1 upon p minus 1. Now, in the next example, we have to prove that 0 to infinity e to the power minus x sin x upon x dx is equal to pi by 4. So, start with sin x. Suppose okay, let us write down sin x, Laplace transform sin x. L of sin x is given by 1 upon p square plus 1, which is equal to f of p. Now, limit x tending to 0 sin x upon x is equal to 1, which is a finite quantity. So, therefore, L of sin x upon x is given by integration p to infinity fx dx, which is integral from p to infinity 1 upon x square plus 1 dx. Integration of 1 upon x square plus 1 is tan inverse x, p to infinity. So, tan inverse infinity minus tan inverse p, pi by 2 minus tan inverse p, which is equal to cot inverse p. So, that means in 0 to infinity e to the power minus p x sin x upon dx is equal to cot inverse of p. Now, if we put p is equal to 1 on both sides, looking at the result we have to prove, we get 0 to infinity e to the power minus x sin x upon x dx is equal to cot inverse of 1, and cot inverse of 1 is pi by 4. Now, let us take last example based on periodic functions. If f of t is equal to t square, where t lies between 0 and 2, and f of t plus 2 is equal to f of t, find L of f t. Now, because f of t plus 2 is equal to f of t, that means f t is a periodic function with 2 as its period. So, therefore, omega is equal to 2. Now, we have already stated this result. L of f t is equal to 1 upon 1 minus e to the power minus p omega 0 to omega e to the power minus p t f t dt for periodic functions, where omega is the period. So, we have L of f t is equal to 1 upon 1 minus e to the power minus 2 p, in place of omega put 2, integral 0 to 2 e to the power minus p t, and in place of f t we write t square. And now, we have to integrate it using integration by parts. So, we get 0 to 2 e to the power minus p t square dt is equal to 2 upon p cube into 1 minus 1 plus 2 p plus 2 p square e to the power minus 2 p. So, put value of this integral in equation number 1. We get L of f t is equal to 2 into 1 minus 1 plus 2 p plus 2 p square e to the power minus 2 p divided by 1 minus e to the power minus 2 p upon into p cube. Thank you so much.